All right, let's dive into something that's, kind of fundamental in the world of AI. We all have this idea that to make an AI smarter, you just make it deeper. You just keep adding more and more layers. But what if I told you that without a perfect start, adding more layers can actually cause the whole thing to just completely fail? So today, we're going to pull back the curtain and see why that perfect start is literally everything.
So this is the big question, the central puzzle we're tackling. You'd think, right? You have a network, it's doing its job, you give it more layers to make it more powerful, and then suddenly its performance just collapses. It makes no sense. To figure out why this happens, we really need to get under the hood and look at how these things actually learn.
And that brings us to our first big idea, what's called the vanishing signal problem. See, to get why a super deep network can break, you first have to understand how the signal travels through it, one layer at a time.
I want you to imagine a massive, and I mean massive, game of telephone. The very first layer gets the input. Let's say it's a picture of a cat. It then has to pass a coded message about that cat to the next layer, which passes it to the next, and so on and so on. The whole point is that by the time you get to the final layer, hundreds of steps later, it can still tell that the original message was cat.
Okay, so every single neuron in these layers has this little gatekeeper, and it's called an activation function. Its job is pretty simple. It looks at the signal coming in and decides what message to pass along. Now, a really crucial part of its job is to keep that signal from getting totally out of control and just exploding into infinity.
And the key thing to see here is the shape of these functions. You see that classic S curve? What that S does is it basically squashes the signal, keeping it in a nice, neat little range, usually somewhere between -1 and 1. Now, this is awesome for keeping things stable, but believe it or not, it's also the root of our entire problem.
And here's where it all goes wrong. In a really, really deep network, we're talking hundreds, even thousands of layers, even the tiniest, most minuscule imperfection in how you set up that initial signal strength gets magnified over and over and over again at each step. The message gets totally garbled, and you end up with one of two bad outcomes. The signal either blows up, or, way more often, it just fades away to nothing. And this visual just shows it perfectly. Take a look at that bottom row. That's the signal's distribution after passing through 1,000 layers using a standard starting setup. It's totally gone. The message has vanished. By the time it reaches the final layer, the network is basically deaf. There's nothing left to learn from.
So, how in the world do you fix this? Well, the answer comes from this really cool shift in thinking. Instead of just looking at this as a statistics problem, researchers started approaching it from the world of physics, specifically from dynamical systems.
And here was the big idea. What if, instead of just a random start, we could perfectly balance the initial signal? Not too strong so it doesn't explode, not too weak so it doesn't vanish. What if there was some critical tipping point, this edge of chaos, where the signal could just flow perfectly, forever?
And it turns out there is. For any of these S-shaped functions, there is a very precise magic number, they call it omega, that defines this exact tipping point. In the world of physics, this is known as a pitchfork bifurcation. Just imagine a single path that suddenly and perfectly splits into two new stable paths, like the tines on a pitchfork. That's what happens to our signal right at this magic number. It finds a new way to be perfectly stable. Let's take a look at what that means. So here, the signal strength is set just a tiny bit below that magic number. And you can see it, right? No matter where the signal starts, every single path just gets sucked down to 0. This is our vanishing signal in action. The message dies. But now, look at this. This is the aha moment. When we set the signal strength to the exact magic number, something incredible happens. The signal is perfectly preserved. It doesn't matter how many layers it passes through, 100, 1,000, theoretically infinity, the information stays completely intact. We found it. This is the edge of chaos. Okay, so this is huge. We found this magic tipping point. Now, how do we actually use it? Well, the researchers came up with this really elegant two-part recipe to give the network this perfectly calibrated start. And it's just beautifully simple. First thing you do, you set the main signal strength at every layer to that exact magic number, omega. Then, for step 2, you inject a very, very small but very precisely calculated amount of randomness or noise. So let's break that down. Step 1. That's our foundation. By setting the main signal to omega, we are placing the network right on that delicate knife's edge we just saw. This makes sure that the core message, that cat signal, can travel all the way through the network without just fading away. But, just being stable isn't enough. A network has to actually learn stuff, and that's where step 2 comes in. That little bit of calibrated noise gives the neurons just enough wiggle room to explore and learn all the different interesting features from the data, but without knocking the whole signal off that stable edge of chaos. So the theory is really cool, but the big question is, does it actually work in practice? Well, let's take a look at the results, because they are, wow, they are seriously impressive. Okay, remember this? This is our before picture. The standard way of doing things. After 1,000 layers, the signal has completely flatlined. The network is totally useless. And here is the after. This is the exact same network, 1,000 layers deep, but started with this new, perfectly calibrated method. I mean, just look at that. The signal is healthy, it's strong, it's beautifully spread out. The network is alive, it's buzzing with information, and it's ready to learn. The difference is just night and day. And this shows us that the new method isn't just a little better, it's way more robust. See all that dark red on the top chart? That's the sweet spot. That's high accuracy. Our new method nails it across a huge range of settings. Now look at the bottom one, the old way. It only works in this tiny, fragile little window. Anything outside that, and it just breaks. This also solves the other famous problem, the vanishing gradient problem. So gradients are basically the learning signals the network uses to get better. And as you can see, the blue lines, that's our new method, they keep those learning signals strong and stable all the way through all 1,000 layers. The orange lines, the old method, they just fizzle out and disappear. No learning can happen. And at the end of the day, all this theory translates to much better performance on real-world tasks. This chart shows accuracy on a pretty tough image recognition test. Our method, the blue line, it just cruises along with high accuracy as the network changes size. The other standard methods, they hit a peak and then they fail, just dramatically. So to sum it all up, the old methods were just brittle, like a house of cards. You had to get everything just right or they'd fall over. This new approach is incredibly robust. It lets us train networks at these extreme depths and scales that were just totally impossible before. It's unlocking the potential for AI that is way more powerful and way more capable than we ever thought possible. This whole story is just such a beautiful example of how rethinking one single fundamental assumption that starting randomly is good enough can lead to this huge leap forward. It really makes you wonder, what other core ideas in AI are we just taking for granted, waiting for someone to come along with a more elegant, physics-inspired solution?